This video is on rotational dynamics. Newton's second law, for translation, we remember, says that the net force is equal to the mass times the acceleration. The rotational analog of Newton's second law is the rotational analog of force is torque. The rotational analog of mass is moment of inertia, and the rotational analog of A is alpha. We've seen those equations before, but now we're going to use this equation on the right. That's what we mean when we say rotational dynamics. You can see the picture on the right side there. We have a uniform disk nailed to a wall through its center of mass. The nail is frictionless, we're assuming. A string is wrapped around the disk, and a constant horizontal force of 16 newtons, you can see, is applied to the string. And we want to know the disk's angular acceleration. So what we're after is alpha. And how are we going to do that? Well, I think one thing we need to note is that we have a disk here. And the moment of inertia of a uniform disk, we derived this in an earlier video, but you can usually look it up in a table, is equal to 1/2 times the mass of the disk times its radius squared. If we want to know the angular acceleration, we're going to have to do Newton's second law. So let's do that. The net torque is equal to the moment of inertia times alpha. What's the net torque? The net torque is this force, 16 newtons, multiplied by the lever arm. The effective lever arm is at 90 degrees to the force, and that's just the radius, so that's going to be 2. On the right side then, the moment of inertia of the disk, let's go ahead and write it out, 1/2. What's the mass of the disk? It's 4. And the radius of the disk is 2, so I need to square that. There's your moment of inertia right there, and we multiply by alpha. Can we do that in our head? What do we get on the right side? The right side we get 8, and here's 32, so I think 4. Alpha is equal to 4. Remember, linear acceleration is meters per second squared. Angular acceleration is radians per second squared. So there we go. If we want to put a direction on that, we could put a little kind of curved arrow like that. We can say it's going to be clockwise. You can tell by the picture. Is part B constant with time? Yes, it is. And the reason for that is that tau is a constant 32 Newton meters. You can see on the left side here, tau is 32, 16 times 2, and that's not changing with time, it's constant. So if the torque, the net torque is constant, then the angular acceleration is also constant. If there were friction from the axle, what would that do to the part B answer? It would decrease it. Friction would provide a small, perhaps, torque in a counterclockwise direction, opposite the applied 32 Newton meters. And so our value of alpha would be somewhat less if we had friction.